So far we have spoken about a couple of theoretical things, a couple of real life things, like we have seen how some real life components are done. So now we have to put our hands on what is called the real electronics, which is the study of the circuits. So here we have two very simple circuits with a couple of symbols. So this symbol here, this wavy thing, is the resistor. We said that those are wires, ideal wires having zero resistance, so perfect conductors. We said also that if we take a component like this, these are lumped elements, so for us all the resistance of this resistor is embedded in the body of the component. Here we have a negligible resistance, similarly on the schematic diagram here. So we consider that all the properties of the components are embedded inside the components themselves. Here we have a battery. This thing is a battery. And here what I underlined with these dots are the charges moving in this circuit. So I attach a battery, some current will exit and it will enter in the resistor, then it will exit from the resistor, it will re-enter the battery. The job of the battery is making charges moving, so it will push the charges from the other side, and here we have a motion of charges which I call current. So we have to understand one very important thing. So really what moves in a piece of wire are electrons, and they are negatively charged. But in electronics, for historical reasons, we don't think of moving in negative charges, but moving positive charges the opposite way. So there is a so-called physical current. I draw this current from right to left, which are made of physical electrons moving, but we consider some kind of virtual, let's say, positive charges moving the other way around. So we can do this because of the electromagnetism. So the effects of a negative charge moving in one direction would be the same of a positive charge of equal amount moving in the opposite direction, and we call this the formal current. So the physical current is made of electrons, but the formal current is made of non-existing positive charge equivalent to the electrons moving in the other side. And this is important because in every textbook of electronics, in every whatever you can find, you will always speak about the formal current. So here we have another circuit where in place of the voltage generator we put another symbol, which is the current generator. So on the left we are setting the voltage and a current will flow according to the circuit and to the model of the components. Here we do something else. We set the current and we say a voltage drop would be established between this lead and this other lead of the components. So we need to speak about those things and to formalize all this framework. So the first thing in order to formalize this is to give a couple of laws, which are called the Kirchhoff laws. These are the fundamental laws of electronics. So speaking about currents, the first law tells us that if I consider a node, and if I consider many branches of a circuit converging to a node, the algebraic sum of all currents converging to a node is 0, which basically means that the charge cannot be accumulated in time in a node. So if there is a current moving in and another current moving in, the algebraic summation, it means that this plus this has to be equal to that plus that, or algebraically the summation of the currents taking into account their direction should be 0. And basically this is something that has to do with the conservation of the charge. We cannot create or destroy a charge, so the charge must be conserved, and therefore we have the first Kirchhoff's law. The second one is a little bit more subtle, and it has to do with the laws of the electromagnetism, more specifically with the fact that the electric field is a conservative field. And it tells us that the algebraic sum of all voltages along a mesh is 0. So what's a mesh? The circuit is a graph made of nodes branches, and when you see a closed loop of branches passing through some nodes, this thing is called mesh. So you can interconnect the things the way you want. You will be always able to identify meshes in your circuit. So this law is telling us that if I consider a given mesh, the algebraic sum, meaning the sum of all voltages of all voltage sources, here we have a battery, plus all the so-called voltage drops across the component should be 0. So what is a voltage drop? Here we have resistors in this circuit. Voltage drop means the voltage that I can measure across a component which has two poles, which is called also a bipole component. Also capacitors and inductors are bipole components. For the resistor we have a model which is the Ohm's law, which tells us that V equals R multiplied I. So if I know the current flowing in a resistor, I can calculate the voltage drop, which I can write it like this, V across it, by using the Ohm's law. I can use it also vice versa. If I know the voltage drop, I can calculate the current flowing in the resistor. So with those two principles, we can do one thing, which is what is called solving a circuit. So here we have a circuit. There are different ways of solving a circuit, but I believe that the most interesting one is what is called node analysis. So first of all, let's say better what we mean by solving a circuit. It means that we give the topology of the circuit, so the circuit itself, let's say the connection, the schematic diagram, how the things are interconnected each other. We give the value of the components. Here, for instance, we see a voltage generator having a value, a battery of 5 volts in this case. We give the value of the resistors. Here in this simple circuit we have only resistors besides the voltage source. So we give the resistance of each resistors, and we are interested in calculating all currents in all branches and all voltages at all nodes. So this symbol here, which is sometimes drawn like this or like that, It's called ground, also GND as an abbreviation. It's a flag. That means that for us this node has 0 voltage. It's like when you want to measure a distance with a ruler. So a distance between one point to another one, like the length of this pen, for instance, we define this to be our 0. The same thing happens with voltages. We have to define which is our 0. It can be any node, but we have to say which one it is. Okay, so let's try to solve this circuit with this method. So I do this, I take a snapshot. Okay, then I save to the photos. Then let's see if I can do this. I want to switch to our blackboard. Okay, and then I want to put a picture, this one. Okay. Okay, so let's see how it works. We first have to identify the meshes involved in this circuit. So here we have 2 meshes. One is this one is this one, and then there is a third hidden mesh, which is the one which is closing this path. Okay, so now I consider the 2 meshes. I call the one on the left A and the one of the left B, and the method works this way. I define a verse of gyration of a current in this mesh. So I assume there is a certain current flowing in this mesh and also in this one, and I give to it a direction. Can be this one or the opposite one, doesn't matter which one. If for instance I will calculate the current in a component and it turn B to be running in the opposite direction, I will have a minus as the result of my calculation. So here what I can do, I can use the Kirchhoff Principles. So I start from the first mesh and I calculate the summation of all voltage drops in the mesh to be 0, which means that the voltage of my source V1 should be equal to the voltage drop across R1, which is R1 IA, according to this current that I supposed to be there. This is the Ohm's law applied to the R1 resistor, plus R2 multiplied the current flowing inside R2. So that current has 2 contributes, one from IA doing this and the other one from IB doing this. So they are one against each other. So I write IA minus IB. Then I have another equation for the second mesh, which is that the voltage drop across R2 now this time is R2 multiplied, I am on the mesh B, IB minus IA plus the voltage drop across R3, which is R3 IB, plus the voltage drop across R4, which is R4 IB, must be equal to the summation of all the voltages of all the voltage source within this mesh, but there are none, so it's equal to 0. And those two things makes a so-called system of simultaneous equations that we have to solve for the current IA and IB. So two equations and two variables. Once I have obtained IA and IB, I can compute everything I need, because for instance, let's say that we already done this and I calculated IA. So if the question is what is the voltage at this node respect to this one, then it is the voltage of the battery minus this voltage drop across R1, and the voltage drop across R1 is R1 multiplied IA. So I can calculate the voltage at this node. Similarly, I can calculate the voltage at this node, because once I know this one, the voltage here is this voltage minus the voltage drop across R3, which is R3 multiplied IB, and so on. So of course I can also calculate the current inside R2, because it's IA minus IB or IB minus IA, and then I have to be careful in order to decide which is the direction, if it goes up or down according to the sign of the current I defined from the very beginning. But the magnitude of that current is the difference between the two. So if I know IA and IB, I can know whatever quantity I want to know in this circuit. So it's easy to solve, but I just want to mention one thing which is useful to notice, which is this thing. So I can rearrange those two equations in a different way. Okay, let's do it. Okay, it's like this. So I want to develop a little bit these calculations. So I write P1 equals R1 plus R2 IA minus R2 IB. I just put the IA terms together, and then I write 0 equals minus R2 IA, sorry, let me write it like this, minus R2 IA plus R2 plus R3 plus R4 multiplied IB. So this way I can do one thing. I can realize that this is a vector of voltages V1 0, and here I have this R1 plus R2 minus R2 minus R2 R2 plus R3 plus R4 and matrix multiplied IA and IB. So if I compute the row by column products, this means that V1 equals this multiplied IA plus this multiplied IB, and I get the first equation, and then it means that 0 equals minus R2 multiplied IA plus all this term multiplied IB, and I get the same equation. But if I write it like this, then it becomes more evident that this thing is a vector. I write it here like in bold. V equals a matrix R multiplied a vector I. So it's again the Ohm's law, but in a matrix form. So all circuits can be reduced to this form, where you have a vector of voltages, a vector of currents, and a matrix of resistances. In the case of circuits made only with resistors, we will see later that there is a generalization from which we will get that we will arrive to a new concept which is called impedance, which is a generalization of the concept of resistance, which takes into account also the behavior of capacitor and inductors. But this thing is very good because this method can be used to make computers solving the circuits. It's just a mechanical thing. You don't have to think. You identify the nodes, you write the equations, you put them in a matrix form, and then you can easily solve this thing with computers, or by hand if you want also. So it's a powerful method. So now let's go back to the slides. Okay. So now you have an idea of what you can do in electronics. So here we have a couple of circuits which are very, very elementary. They are called the series circuit and the parallel circuit. So here again we are doing things in a very simple way, only with resistors for the moment. So by series it means that the components come one after the other one, like those two, and by parallel we means that they are arranged in a parallel fashion like this. So one question that we can think of is the following. Let's say that this thing here is a black box. So I draw it here, something like this, and we have a battery, positive pole, negative connected to this. So inside this thing there is something, but from the point of view of the battery, the only thing the battery, if we impersonate a battery, let's say, the only thing a battery can know is that there is some current going in and some current I going out, and it's the same for this conservation law, I mean the Kirchhoff Principles. So one question is, can I replace whatever is inside here with something else that produces the same current here. So if we can do this, and the answer is yes, we can do it, then this secondary circuit is called equivalent in this sense, that it will produce the same effects in the external world, which now is represented by the battery. So this is the new question we want to answer. How can we compute equivalent circuits? So now we can do this, because if we go back now to our scratch board. Okay, let's go here. Okay, let's try to make the series circuit. So we have a battery, we have one resistor, another resistor, and we close the circuit. Then the Kirchhoff principle will guarantee that a current will flow in it. I call this current I, and I call this resistor R1, this one R2, and the battery I call it V. So if I take the voltage drop across R1, I call it VR1. This is equal to to R1 multiplied I, the Ohm's law. The voltage drop across R2 similarly is R2 multiplied the same current I. And therefore, if I summate the two, this should match the voltage of the battery in this mesh because of the Kirchhoff principles. So V equals VR1 plus VR2, which is R1I plus R2I, and with very little algebra I can put R1 plus R2 together, and then if I read this thing here, again it's the Ohm's law for a so-called equivalent resistor, which is R1 plus R2. So for this circuit, V equals R equivalent I, with this R equivalent. And then we found that the equivalent resistor of a series of resistors is just the summation of the two values. So we can substitute those two resistors for a resistor having this value, and the battery will not understand we did this modification from its point of view. So similarly, we do the parallel. So let's take a battery like this with voltage V. We put a resistor like this, R1, then we create another mesh and we put a resistor R2 like this, and this time we can notice that the same voltage V is applied at both this resistor and this one. Remember that this is a perfect conductor, so this node here is the same of this one, and this node here is the same of this one. So there is a current I1 and a different current I2 flowing in those two branches, but by making use of the Ohm's law I can calculate that I can write that V equals R1 I1, but also V equals R2 I2. Okay, and then I2 is the current flowing in the resistor R2, which is the current flowing here and also flowing here. So by using the first Kirchhoff principle, I can understand that at this node, for instance, those two currents are exiting, and therefore there should be an entering current, which makes the algebraic summation of the currents at this node to be 0. So I call this current I total if you prefer, let's say I. So I equals I1 plus I2. And therefore this current is also here because it merges here. And so if I'm able to calculate this current I, then I can calculate an equivalent resistor using the Ohm's law applied, let's say, to this bipole node and another node, by saying that this should be equal to R equivalent I. So let's try to calculate this current I. So the current I1 is equal to V over R1. The current I2 is equal to V over R2, and I is the summation of the two. So I equals, I put V in common, and then I write 1 over R1 plus 1 over R2. And so, therefore, this is exactly what I was looking for. I just recognize that this equivalent resistor is 1 over R1 plus 1 over R2. So the reciprocal of the equivalent resistor is the summation of the reciprocal of the resistors which are in parallel. Sometimes it is useful to consider this quantity G equals 1 over R, generally speaking. This thing is called conductance. So coming back to the presentation, what we can say about this is that the equivalent resistor of a series of resistors is the summation of the resistances, while the equivalent conductance of a parallel of conductances is the summation of the conductances. So we don't do this, but we can also do this. We can say that our equivalent series is the summation of the resistances, and G equivalent parallel is the summation of the conductances. It works for any number of resistors in series or in parallel. So then there are also other methods which are useful to know, and we will do this on next time. So thank you and see you next time.